Hello again, folks. Today we're going to be doing the last section for the semester, which is section 10.2, the law of cosines. Right? Another slew of formulas, basically. All right, now, I redrew the sort of diagram that I have to summarize. These pieces of information are still pertinent. They're still important. Know the Pythagorean Theorem, of course. You can get away with basically knowing sine and cosine. I didn't do tangent. I would have liked to, but I really did run out of space. Anyhow, this is old news, all right? Old hat, you know, as far as we're concerned. Last time, if you were able to watch, this was basically what was covered in section 10.1, the law of sines, all right, and the area of a triangle given two sides and one angle. I want to say that it has to be a specific angle that you need to have. All right, one at least that is different from, it's not related to the other two sides. All right, so for instance, if you look at the, I'll sort of flash this again. If you examine the formulas here for areas of oblique triangles, all right, it's still 1/2, and you notice in here they have BC and then alpha. Think of it as BCA, and in this case it's ACB beta. All right, and AB gamma in this case, which you can understand. It's not really translated to C. I believe it's G if the name is any indication. Kappa is K really, but it'd be closer to C at least. Anyhow, think of this as some array or derivative of ABC, 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 right? When you're trying to use the area of an oblique triangle formula, all right, you'll be given two sides and one angle potentially, but you want it to be those three distinct parts somehow, right? B and C and A, the angle A, all right, and the other two are sides, or, you know, vice versa, you know, that you have A and B, and then C is the angle instead. Right. Anyhow, for today, all right, before I put this down, this is the material that we'll be covering, the law of cosines, these three, and then something called Heron's formula, which is for areas as well, if you happen to know the perimeter, which means that you would need to know three sides. All right. So this will be basically the subject of section 10.2. These two things specifically. Well, cosines, Hero or Heron's formula, depends on which textbook you're reading, what this poor person's name is. Perhaps it's a bad translation to English. Okay, so moving on here. Let me give you another diagram to sort of re-emphasize the usages of laws of sines specifically in comparison to the laws of cosines, because they're very similar. All right, the original drawings that you were given. All right, so I'll erase this much here, and then I'll draw some examples of triangles along the top here. Okay, so I'll use green just because green happens to be pretty faint, and I really don't want to emphasize the sides so much as I want to highlight them in a moment. All right, here's a triangle, a generic looking triangle. Here's a third one, second and third. And then, if I'm a little bit more strategic, perhaps I can fit in. I want this to fit nicely. And that's brilliant. Just erased everything. Gotta make them smaller. There you go. It's a little bit better. I find writing on that side of this makeshift board a little bit more problematic than writing on this side for some reason. Maybe, perhaps because I'm stretching. Okay? You know, I'm trying to have pretty set three triangles here. And hopefully that's not too faint. Okay. So I'm going to make that a bit darker. Green is a lovely color, but not when it comes to writing. It's very ferociously windy today. I don't know if you can hear it. Okay, now, I'll use blue, perhaps black, to emphasize. All right. In the first situation, suppose you are given an angle, and there's a second angle, and there's a side dimension. So just to emphasize this situation, two angles and a side between them. One angle, a second angle, and then the side is not between them. So here, red and green are always trouble. And lastly, this situation, where you have one angle and two sides. Okay, now as discussed last time, this is abbreviated, these situations, according to the initials of the measurement. So if this is an angle, this is referred to as angle. If this is a side, this is a side. And if this is an angle, this is A here again, ASA. This is in a very subtle way implying exactly what the drawing is indicating, which is that the side is between the angles given. So you might summarize it like so. Side between two angles. For that situation. Next, this blue is a bit faint, so I'll use another one. An angle, and then a side. And to distinguish it, if you were to describe it, it would be a side not between two angles. And then there's this last situation, at least last according to last time. All right. And this is the one that makes me chuckle because I have a juvenile sense of humor, because the initials are arranged not to be humorous, all right? Side, angle. Even though I've been reading things counterclockwise, starting from here, I'm now going to read counterclockwise starting from here. In this case, you would say that it is an angle, not between. Two sides, as opposed to a side not between two angles. Just to complete that thought. Okay. Okay, now, and again, collectively, these are very faint. The law of sine, or the law of sines, right, which is essentially just ratios. Right? Sine of an angle, let's just call it A, is equal to, pardon me, the sine of an angle over its side length. You know, it's a related side length, the opposite of this angle, basically. Could be part of or rigged as part of a proportion equation in which the sine of the second angle over its respective or related relevant side length is sine of b over b, and you could in fact write a third one for the third angle and the third side length. This is the most practical usage of this, right? You, unless it's otherwise written, you could specify what the labels actually are. Just make sure that you identify them correctly. Right. When we talk about the side lengths, the side lengths, if this is A, are always across from it. Across from whatever the angle is. So if you have angle A here, then A would be over here. Right? If you have B here, then side length B would be here. And if this is C, then this would be C. Right? They're always opposite of the angle, the corner, the vertex. Now, this is what we're adding to this because it is very similar, and that's the whole reason why I'm bothering to draw this. When we talk about law of cosines, there'll be different formulas than just these ratios, these proportion equations, but what you are given is similar looking. So if you have this situation where you have a side, an angle, and then a second side. That's a bit faint. All my blues suck today. What is going on with blue? Alright, and again, if you're sticking with the sort of the nomenclature of how we label these things or distinguish them, alright, it's a side, an angle, and then a side. Not to be confused with this. This is ASA, this is SAS. Again, to distinguish it verbally, this is an angle between two sides. And then this last situation is three distinct side measurements, no angle. Fade it out really bad. Okay, that's better. There we go. I'm putting these tick marks just to indicate that they are, ideally, they don't have to be, I suppose, but three distinct measurements, whatever number they are. In this case, it is side, side, side as the abbreviation. This is three sides, no angle. Given. Okay, so essentially, if these situations pertain to law of sines formulas, right, then these two situations pertain to, or you will utilize law of cosines. And they are a more complex formula, but they're derived from basically Pythagorean Theorem. I'm going to show you an example in a minute. Okay. There are three. Depends on what situations you're given, what measurements specifically. Perhaps I will write them just here really quick. A squared is equal to b squared plus c squared minus 2bc cosine of a. I like a as opposed to alpha, just a preference, but it doesn't have to be. This is the argument. That is the angle. Lowercase letters are for side measurements, and capital letters are, for all intents and purposes, the angle measurements instead. Right? And any one of these that you would see, there's two more, can be rearranged to solve for an angle if you needed to. Inverse, formula, pardon me, the inverse function. Okay. B squared would be this arrangement. A squared plus c squared minus 2ac cosine of b, angle b, and c squared. A squared plus B squared minus 2AB cosine of C. Okay. Now, bear with me because I want to verify I've not written something incorrectly. I'll stand back to look at it. Let's see. A squared B squared 2B. Looks like it's good. Okay, good. All right. That is really a summary of these two things, right? And again, we're going to be discussing the usage of the law of cosines today. You might at some point have to incorporate the law of sines as well, but you know, that's up for grabs. Just make these distinctions. Right? If you were given a side, an angle, and a side in that order, or a side, and a side, you're going to be using this at least to start with, right, rather than this. If you're given these situations, use the law of sines. Okay. Now, if you're curious where this came from, as I mentioned somewhat vaguely, it's derived from the Pythagorean Theorem. So just say hypothetically you had this situation. Some triangle that looks like this. And to kind of help it along, let's put this on a coordinate plane so that one of the vertices is at the origin. Right. We know at this point that if this was along the edge of a circle, a unit circle, right, that what would ordinarily be the coordinates x comma y are instead the cosine of the angle theta here times r. Right? And if it's a unit circle, then it's just cosine. Okay. And in the case of y, y would be the sine of theta. Now why is that? If the ratio for sine is opposite of this angle, and usually opposite is along this perpendicular edge here of an imaginary right triangle, and this is y, right? Then the ratio of opposite over hypotenuse is appropriately y over r. Now it just so happens that if it's a unit circle, the r value is 1. So that means that sine of the angle here is just really y. Right? And in a similar way, if cosine of theta is really the relationship or the ratio of adjacent over hypotenuse, then in this context, the x value would be from the origin to where this perpendicular, imaginary perpendicular edge would be. This would be x, right? Representing that coordinate, right? If it's adjacent, we're talking about a dimension that is a linear dimension adjacent to this angle here. Just getting a little more sloppy. Then it would be x over r. And again, if it's a unit circle, then the r appropriately would be 1, which means that cosine of theta is just simply x. Right? So we could substitute in place of x cosine of theta, and substitute in place of y sine of theta. And although that is a little bit awkward, those would be the coordinates of this point here. Now, the thing that is in blue is an oblique triangle. I'll just shade it to make it a little bit more obvious. this is an oblique triangle. I'm going to erase out the points that are not relevant right now. If we want to basically translate the Pythagorean theorem, I'll erase this just for the space for a moment. The Pythagorean theorem is c squared is equal to a squared plus b squared, right? The sum of the sides of a right triangle squared is equal to the hypotenuse squared, right? If we want to translate the Pythagorean theorem, which is for right triangles, right? And this thing shaded in blue is not a right triangle, it's a non-right oblique slanted triangle. Then what we would need to do is incorporate the trigonometric relationships here at some point, right? You have to do a little bit of translating in between. Normally, what is A, you might say, is the altitude of this. So it would be what y is, right? Just to change the labels for a moment. And x is the b value. It's the bottom of this slightly larger imaginary triangle here. This would be x squared. And I'll leave c for the time being. Let's see. Okay. All right. What gets a little hairy is a lot of these superimposed pictures, which this is why I'm hesitating. I'm trying not to make it too complicated. It really doesn't have to be if I do it right. Let's discuss this chunk of this larger right triangle, which I will now sort of scribble in red here. The y dimension would be easy to substitute. The y dimension would be sine of theta squared, and if it happens to be part of a circle that is not just a unit circle, right, then it would be r. Like instead of like if I had y over r and I just pretend that it's not 1 for a second, all right? If I solve this for y, r would end up over here. So in some situation where we have to take into consideration the radius as something bigger than 1, then you might adapt this to just, compensate. Put r instead of not bothering to. The reason you wouldn't normally bother to is because it usually is just 1. Right? But I'm going to put r here for the time being. Okay. The x dimension is a little bit more complicated. The x dimension is a little bit more complicated because if we're trying to figure out not the whole thing across, not just from here to here, right, but just a chunk of this, like it's inappropriate to say exactly halfway because it isn't, right, but some smaller portion of the imaginary right triangle, right, it would basically be the blue, all right, subtracted out of this. This chunk here would be, let's just call it some of the letter. Let's call it C, all right, just not to confuse it with anything else. to use C. I don't want to keep changing the labels too much. So I don't want to confuse it with this, because it's unfortunately what the problem is when you're deriving this is that if you don't choose the appropriate labels up front, it will get hairy. All right, so I'm going to reluctantly go with the letter C for a minute. Just don't assume that this C is this C for right now. Maybe a D would be better. I'll put a D here. All right. The rest of it, the red portion of this X, is the whole thing is X. And this portion here and here would be the difference of the whole thing minus the chunk that is just from here to here. So if this, I use my hands here for a moment, if from here to here is X, what represents this much, and this is what I'm after for right now for the sake of the Pythagorean theorem, it would have to be this portion subtracted from the whole. So let's just call it temporarily X minus D. I hate to use that label, but I don't want to confuse it with this for the time being. So the X dimension that I'm substituting in here, this is still plus because of the formula, is what is the cosine. In a similar situation, if I assume for a moment that cosine is not part of a unit circle, right? If I wanted to not just assume that R is 1, then in order to solve this for X, that is to isolate X, I would end up having to put R over here, which means that in some other situation where I can't ignore the fact that R is usually 1, I'm going to compensate by just temporarily putting it here. So what does that mean? It means that this X dimension, which is really R times the cosine of the angle, right, minus this chunk of it, which I'm just temporarily calling D, is this much of the triangle here. So what I'm going to do is I'm going to take this out of here for a moment and just draw it next to it with its respective dimensions to make it a little bit more obvious. This is now temporarily X minus D. This is still Y, right? What is Y? The radius, assuming that it's something other than 1, times the sine of the angle squared. What is the X dimension here? It's really because it's a fragment of the larger triangle. It's the whole thing X minus D. What is X? It's R times cosine of theta minus that extra chunk. Okay. Now, let me finish some of this else. This C value, which I have dropped for this up to this point, I'm just going to write here. And according to the original labeling here, it was R. I'm going to have to go back and change it at some point eventually, but I'm going to call it what it is for the time being. It's R squared as opposed to C squared. All right. And then I have this, all right, which I should remember to put the squares in both cases. Okay. Now what I could do is drop the parentheses for a moment. After I would basically, if you squared this, you know, what would you have? You would have this exposed would be R squared, because it would apply to both of these, times the sine squared of theta. This one is a little bit more problematic because you would get the perfect square trinomial model basically would be this factor times itself. So what would you end up in that case? You'd have a big mess. the result of squaring this would be that you would have the first term squared. I might write in blue just to make it distinct. R squared cosine squared of theta. And then the middle would be twice the outsides. So if it's minus, it would be minus 2 RD cosine of theta. And then it would be plus d squared on the edge. Okay. All right. If you take the time to factor a little bit, all right, and I'm going to sort of underline to kind of help along here. I know that I wrote these in different colors, but these things that are in black and in blue here are really next to each other. And I'm only squeezing it in because I'm running out of board space, unfortunately. If you pay attention to just these two terms, right, notice something. They have a common factor of r squared, even though they came from two different factors. Right? You could factor out the r squared then, in which case you would end up with this, r squared, and then it would be sine squared of theta plus the cosine squared of theta, and the rest of this blue stuff here would be left over. It would be minus 2 RD, just because of my labels, cosine of theta, plus d squared. Right. This, which is written in blue here, is underneath what I have tangled with here. Now, it just so happens that sine squared of theta plus cosine squared of theta is a trigonometric identity, right? It's the Pythagorean identity, right? Sine squared of an angle plus cosine squared of the angle is the amount of 1. I have weirdly an ant crawling up my camera, and hopefully he won't crawl over the lens. I don't want to mess with him. Dude, why? He likes my thing. Anyhow, the amount that you see here will reduce to 1, which means that this is r squared times 1 minus 2RD cosine of the angle plus d squared. Okay. Running out a little bit of space, so I'll erase this here. Alright, now what ends up happening is this. R squared times 1 is just R, right? Squared, right? If I purposely take this dimension here, d squared, and move it up to the front, right? And what I end up with is this, R squared plus d squared minus 2 R times d times the cosine of the angle. Is equal to what the opposite side was. I'm going to go back and now use the, I really shouldn't have bothered writing this here. I'm going to go back and just use the original label, right? C squared here. All right. This is one of the 3 incarnations, basically, of the law of cosines. The only difference between what I have drawn here and the 3 that you have written on your paper is that on the paper that's typed, the labels are changed entirely. I haven't really gotten to it, all right? I have changed them to what they needed to be, all right, in order to be a little bit more clear than using R's and D's and different things. I went with that because I didn't want to confuse the dimensions of one triangle with another one. Anyhow, what this would translate to, if it is in fact c squared, right, is this, right? A here instead, right? B here instead of D, right? And then instead of R and D, A and B. Right. And then cosine of the angle that would be relevant in this case would be C in this instance. If you rearrange this for B squared, right, again you would see it would be A squared plus C squared instead, minus 2AC cosine of the B angle instead. If you did this for A squared, you would have the arrangement of B squared plus C squared minus 2BC cosine of the angle A. The unfortunate thing when you're deriving this, if you're not very careful, and apparently I wasn't careful enough, all right, is that you don't want to let with the letters that you're choosing confuse you, right, in the middle of the derivation, right? Anyhow, do have the sort of flexibility of mind to go that calling it one letter versus another is not really important, right? As long as it refers to the same dimensions. Right. Anyhow, this is the basic process, however sloppy that it is. Right. It would help, as I often complain, neatness, right, is what makes you derive something clearly. Right. So if you try to do this at home, all right, do it on a much bigger surface to write on. Right. And be careful with your labels. Right. These labels are not wrong. All right. They're just unfortunately not A, B, and C. Right. This is what they would work out to, right? Those two dimensions added, squared, subtracting the same two dimensions, just calling them different labels, right? And then cosine of whatever the angle is. Okay? Now, enough of that cumbersome stuff. Let me give you an actual example. So if you had, this finally is an example. It might be getting a little dark, so I don't like the reflection. If you had to find the unknown sides and angles, that is, solve the triangle given, which basically means, i.e., find missing parts. Let's examine what would be given here. I'll draw a triangle again. This black is fake. Here. Here is a generic looking triangle. We already have established formulas, and we might choose either this one, or this one based upon what the labels are. So if we have an angle here, right, and they just simply write 10 here, and then an angle here that is actually written, that's 30 degrees, and this is a third angle, and this is written as 12. Let's take into consideration what angles and what appropriate side dimensions are actually given. Right? If you have just the letter A, this is actually to my advantage now. If I have just the letter A written here, across from it would have to be an A value. So we'll just designate it as A is equal to 10 specifically. If across from this C would have to be the C value, then let's call this C is equal to 12. Right? That means that across from B, although the actual measurement is given, B would be the unknown in this case. And I would compile a list. So I would say, all right, if I'm going to solve the triangle, then I got to get all the sides and all the angles. So let's make two lists. All right. Sides, angles, and how we will go about the process. Okay, and I'll put in red the things that we actually know. We technically know side A because of this relationship. It is across from what would be vertex or angle A. So I'm going to call A is equal to 10. I'll put red things we know. Right? C apparently we also know. And that's 12. B we do not. So I'll put that in black. And of angles here, what do we know? We know only angle B, and that is 30 degrees. Then therefore we do not know what angle A is, and we don't know what angle C is. Okay, so we got just exactly half of the information that we would need to know total. All right, now let us see if we could apply this to the law of cosines specifically as something of a strategy for deciding that. All right, remember, we have law of sines and law of cosines. If you are given these situations, angle, side, angle, known, or angle, angle, side, known, or side, side, angle, just for politeness. If these dimensions are known, you would appropriately choose the law of sines formulas instead. The ratio of the angle and the side dimension that is related equal to the angle and the side dimension that are related in a separate ratio. It's a bit verbose way of saying it, but I think you know what I mean. The formulas that look like this. All right, a fraction set equal to a fraction. If, on the other hand, you have these two situations, side, angle, side, and side, 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 you would appropriately choose the law of cosines, which are one of these three. Okay, so let's see what we got. We have I'm going to highlight here. We have apparently a side dimension, because that's a 12 there. We have an angle, and then we have a second side dimension, which is a 10. So this is a side, an angle, and a side. A side, an angle, and a side. This is something that would be peculiar to the law of cosines. So we would have to choose between these three things then, right? And I would go with what the labels are. If you have A and C, then let's go to the incarnation of this that incorporates A and C. They're really all, as you can see, it's just it's adding these two dimensions, multiplying those same two dimensions, and then the only thing that is different is that the angle is the C angle. Right? I would go with this for right now, just because it emulates the labeling of this particular triangle most closely. So I will erase this just not to have it distracting here. And I'll erase this. And I'll re-emphasize. This is the situation that we are given. This is a nice marker. Okay. And this is the appropriate incarnation of the law of cosines. All right. So if I am solving for B, it's already ranged as so. The B by its lonesome on one side. The only tweak that we would have to employ here would be potentially squaring if we want to get the side dimension. Let's insert the dimensions that we have here, 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 and here. And see if we have everything squared away. All right, so this would be 10 squared. and this would be 12 squared, and this would be 10 times 12, and this would be cosine of 30. You could use your calculator, of course, for this situation, but that happens to be a special right triangle. So we could translate this into the appropriate ratio, provided we remember special right triangle relationships. Which is, if you have a 30, a 60, oh boy, and a 90, the dimension that is adjacent to 30, which is what cosine implies, is the square root of 3. Right? The hypotenuse would be 2. So this would be the ratio of square root of 3 over 2, and if square root of 3 is 1.7 something, then it would be half of that. Yeah, 7.07, I believe it is, something like that. Let's see. All right, so I'm gonna get rid of this. And rewrite this a little bit more cleanly here, because again, if I teach you nothing, all right, neatness helps, all right, it'll help you avoid mistakes. So don't limit yourself to a canvas of this size, all right. When you're writing something, write on the wall, all right. Whatever is and don't feel bad about it either, because you need the space to think. B squared is equal to 10 squared. There's no harm in doing that, really, right? Which is really 100. And then 12 squared adjacent to it is really 144. And then this is minus as far as these numbers combined are concerned. Oh, I'll do myself a little favor. I'll write this out. Notice if these are all bunched together, as they would be, right, that it would be strategic to not multiply them, because the commutative property can take hold. If you have a bunch of factors that are basically pressed together, it is understood that they're all just being multiplied together. So, for the sake of efficiency, I could think of these as being all like a fraction with one as a denominator, and then cross out 2's, right? Because that is the common factor above and below, right? And therefore this is b squared is equal to 244 minus 10 times 12 is 120 times the square root of 3. And to get b, you would have to take the square root of whatever this is. Alright, so you would type that into your calculator. Just be careful about the syntax, right, the way that you type it, and you'll see what it is. So, square root of 244 minus 120 times the square root of 3. Close the parentheses, I'll just show it to you now. This is as I have typed it. I put a parentheses, probably unnecessarily, but I couldn't resist the temptation. Eyebrow wiggle. Anyhow, what you would get is this dimension for the b value, right? Because it has an irrational number, square root of 3, expect it to be an infinitely stretching decimal. So unfortunately, we are going to have to round. If they don't specify, all right, rounding to a particular place, then it's your call. All right, do what you intuitively think. My instinct is to use something like 3 decimal places usually, if at least 1, but no more than 3. So if this is, according to the calculation, 6.0128, whatever it is, if you round to the 10th place, then it would just be 6. To be a little bit more precise, let's maybe round to the thousandths place. So based upon 8, this will change to 3. So I'll insert that in here. 6.013 units, whatever it is. Okay. Now, so finding the angles, and I can now put that in the drawing as well. 2.013. I can't pull the old trick of, well, a triangle adds up to 180, right? And then I'll just subtract the sum of 2 angles from 180 to get the third one, because I don't have the majority of information. I only have 1 angle. So when I'm trying to find the angle, I'll have to resort to the law of cosines now. One extra angle. Right. I'm going to use law of cosines, law of sines, which would be basically a proportion equation using the appropriate trig function and the appropriate side dimension. So there's probably more than one way to do this. All right, but I would try to avoid using the dimension that I have rounded. All right, I would stick with the things that are given as they are presumably, exact. Right, and you'll get a better answer if you do that. So let's see. I have no a value here, but I have a dimension here. Looks like it's inescapable in this case, huh? Yeah, that stinks. All right, if I went with this sine of A over A, then I could use the sine of B over B. The only one of these that is truly reliable is none of them, actually, because I have no choice in this case. I have to use my rounded figure. You can, if you want to, store this in your calculator, right? And then when you're going through the proportion equation to solve, all right, you recall the stored decimal number. The only thing is, realize it's going to be very precise because it will be something like 10 decimal places, but it's never going to be exact because it comes from an irrational number. It's unfortunate, but it's just the way it is. If I were to take this and fill in the information that I do have, all right, I have for B a 30-degree angle. All right, for A, I have no clue. All right, that's what I'll solve for. But I do have the A dimension of 10. All right, no matter which way I slice it, in this case, it seems like I'm pretty much stuck having to use what I have here. So just for the sake of getting through it, if I had this 6.013, all right, now I have the majority of information insofar as this this proportion is concerned. Remember, when you solve proportions, it's cross multiplication technique. That is, you multiply diagonally this way, write it out on one side of it equals, it would be 10 times the sine of 30. And then multiply diagonally this way, which would be the sine of the angle, the estimated 6.013 times the sine of A. Try not to do any sort of rounding intermittently. Wait until the end. We want to solve for A, we got to get A alone. The first thing would be to now divide by 6.013, both sides, 6.013, and then you're left with this. The sine of A, which is the argument of the function, is equal to 10 times the sine of 30 degrees over 6.013. Use the inverse because the inverse of sine will give you the actual argument that is the angle in this case. So you would basically enter this into your calculator, 6.013, or at this point recall the whatever you have, whatever form of the b dimension that you have saved, stored. Okay. Anyhow, I'm going to enter it like so, and then I'll show you. The inverse sine of 10, put it in parentheses, 10 times the sine. Remember, your calculator should be in degree mode for this if it was given in degrees. Okay. Divided by 6.013, my rounded up figure. This is what it looks like according to the way I've typed it. The inverse sine of, and then I was very careful with the syntax here. I put the entire top in the parentheses. Notice that there's two parentheses here. On the opposite end of this, you see the enclosure here. And then division, and then the bottom is just the rounded number I have. 6, yeah, there's an error. If you are dodo like me and you put the wrong digit rather than 6, all right, hit the second and then delete for insert, so you don't have to erase this. And then just insert 6, there you go. And then you can delete that. 6.013, good that I checked, right? And this is your angle, 56.2, 5, whatever it is. Oh man, my ant is on my book again. Go ant, go. Okay. Let's see. In theory, because I'm working with a rounded number, I would probably have to round to the same place. All right, so this is what you would get on your screen, 56.2564, whatever it is, into infinity. I would prefer really to have maybe no more than the tenths place. It's just a personal preference. That's not really appropriate if I'm using this number here, but whatever. So this is about 56.2 degrees. 3 if I round nicely. Right. Because of 5, this would be rounded to 3. And now I could pull the trick. I mean, you could go through the same process again. Another trick, another law of sine proportion equation to figure C, but I wouldn't, right? To get C in this case, which looks very stylized, it's like Action Comics font here. Right, that's kind of cool, actually. This is just subtracting the sum, from 180. So if you wanted to get C, it would be 180 minus the sum of these two. 56.3 plus 30, which would give you 86.3, and that will be a C value. Cheating really quick here. Let me get 97, right? 0.7. This would be about 93.7 degrees. Right? These all add up to 180 because of the way that they're rounded. Okay, and these are the dimensions that would be, especially with this approximate here, the side dimensions of the triangle. Okay, you see that even though you start out with the law of cosines, right, whichever one you deem appropriate, and you would have to decide based upon the labels given, or whatever you decide. Like if they don't give you labels, then make the decision for yourself. And then eventually end up using law of sines anyhow. Okay. Let me show you the other law of cosines problem, in which case you're given all three side dimensions. And then we'll use Heron's formula. It's getting so dark. It's not that late, it's just it's threatening to rain. If I have to, I'll put the light on. Okay, suppose you had this triangle given to you, just green again. Is that visible? And it's right in the way of the... I don't know if it's obvious, but I'm doing something that I don't normally do. Not to digress too much. Normally when you teach, you look at whatever you have prepared and you write on the surface. Even though you may face the audience, you're not really looking at them. Because if you stare at people, right, that's kind of weird. You know, like, hey, you, I'm just teaching this one person. You don't do that. Anyhow, when you have a camera, you have to constantly, like a bird, look at yourself and go, ooh, look at me, to make sure that you're in the frame. So it's an added thing that I don't normally think about. And that's screwing me up a little bit, I feel. Suppose that you are given a situation like this, right? That we'll call this A is equal to 20, and B is equal to 25, and C is equal to 18. And this does not form a Pythagorean triple, right? Because if they did, right, then you would just need the Pythagorean formula, and two of them squared added would equal the third thing squared. And that will not happen in this case. Don't even worry about that. Anyhow, if they didn't verbalize it, right? Based upon this drawing and the fact that they're using lowercase letters, this means that what you have is basically three distinct sides. You have a side situation. Right? That is a very faint black. If you have that given to you, essentially, a side, three side dimensions, that means that you're going to use law of cosines, which would be one of those dimensions squared and at least one of the angles. What you can get, right, is an angle one at a time at least. So let's say that we're going to get angle A. Then the appropriate version of this, and I'll point at it on the photocopy rather than draw it again, is the one that has alpha in it. So if you look at the three laws of cosines, they're derivatives. Pay attention to the argument of each of these trig functions, of cosine of A, cosine of beta, cosine of gamma in this case. If you want to get A, right, then let's go with this incarnation of the law of cosines. So A squared is equal to B squared plus C squared minus CB, BC. Cosine of A. Alright. How you would memorize this, if you were inclined to do that, I would say that the same letter is on the outsides. Right? So you have the side dimension incarnation of A and the angle dimension incarnation of A on the ends of the formula. And in between are the other two used twice, squared, and as two things multiplied. And there's always going to be a minus here, and it's always going to be cosine. Anyhow, if you incorporate these into the formula, right, you are going to have a number here. You're going to have a number here, 25, and here, 18, and then those two things multiplied. So let's see, 25 and 18, And then the only thing that is going to be left over and nebulous and mysterious is the A dimension, that is the angle dimension. So if you want, you could move all of the parts, right? I would simplify a little bit, and then sort of use the inverse trig function for cosine will give you the angle. So here's what this may reduce to. You could take the generalized formula, or you could have it with the dimensions filled in, right? It might just be easier to use the generalized formula first, right, rather than worry about these numbers. There's nothing wrong with doing that, but it might be a little bit more cumbersome. If I were to drag A over to here first, then what I would have is this on the right side. I would have B squared plus C squared, and then if it's positive on this side, it would logically have to be minus on this side. If, just to save space, if I were to take this entire term and drag it over to the opposite side, then it would be this. If it's minus here, however ugly and complicated it is, this is one whole term that's being subtracted, then it would logically have to be a positive on the opposite side. That is an A, I swear. And now you could just take advantage of the fact that all these terms are being multiplied, divide all of them at once, both sides. 2BC. They would simplify as such. And you would have cosine of A, which is almost done, over this complicated ratio. The inverse of cosine times this formula that has been arranged, 2BC, will be what A equals. You could, if you want to, again, fill in the numbers and simplify the top, simplify the bottom. If it works out to be a number that is a nice number, then you'll just have inverse cosine of that one nice number, but we'll see. Just be careful if you choose to just enter this into your calculator. Use parentheses appropriately. All right, 25, 18, A is apparently 20. And then this is 25 and 18 down here. Right. It's going to be messy because they're big numbers. So let's enter this. All right. Just be very careful. Start out with the inverse cosine, which is second and then cosine. And then I would isolate the top, use another parentheses, and then type this as you see it. All right. 25 squared plus 18 squared minus 20 squared, 20, not 2. And then close the parentheses here. This may be overkill, but I'd rather be safe than sorry. And then divide by, again, use another parentheses to isolate the bottom, just not to confuse the calculator. 2 times 25 times 18. And then you can close the whole thing. All right, if you get a syntax error, it just means that you didn't put enough parentheses, or maybe you put too many. All right, so what do you get? 2,700, no, that can't be right. It is a serious issue here. Yeah, something went awry here. No. There is a syntax error somewhere. Oh, here's a session. Because I typed 2 and then went, oh no, it's 20. Here's what happened. it didn't automatically erase my squaring, right, when it was over here. It just carried it to the end. So I'm going to delete this. All right. And I'll put the parentheses there. No, don't do that. There you go. This is corrected. No squaring on the end. That's not even what I wrote here. It just didn't type well. Okay. Here you go. 52.4. All right. So this would be the angle A. 52.4 degrees. If you wanted to, if they were to ask you to find the other two dimensions, you can basically use the law of sines at this point. You will start out with law of cosines to get perhaps the angle in this case, and then to find at least one of the other two angles, it's called as B and C respectively, use an appropriate law of sines. So if you have the sine of A over its A dimension, then you could find the sine of B over its B dimension, because you have the majority of information in either of those cases. If you want, you could also do the same thing for C, and it would be that. In which case you would just, the only thing that you're unfortunately going to have to do is use the rounded number here. You really have no choice, right? 52.4, 52.4, 20, and 20, and the B dimension is 25, and the C dimension is 18. This route, again, you're going to have to employ cross multiplication techniques, and it would be 25, the sine of 52.4 is equal to 20 times the sine of B, and in the other instance, cross multiplied is 20, the sine of 52.4 is equal to, oh, pardon me, it's 18 in this case. 20, the sine of C, and if you rearrange this, cross out 20, what you end up having to do is to use an inverse trig function using these dimensions, like so, over 20. Enter this into your calculator, and in this case it's almost the same thing, it's just using a different number here. 20, in this case C would be equal to the inverse sine of 18, the sine of 52.4 over 20. Enter this into your calculator. Curious. So let's see. Clear. The inverse sine of, being very careful as I type this, 25 times, or hopefully 52.4 divided by 20 is that. This is the first one. The inverse sine of 25 times sine of the argument of the angle here. 52.4 divided by 20, and you get that 82.0 roughly. B, if we call this B, right? A is about 52.4. B would be about equal to 82.0. C would be the next one. You could, at this point, attempt to just add these and then subtract from 120 and get the same answer, but let's say you started with this one. if I just tweak this ever so slightly into the same thing, but I'm going to insert 18 in here. It's inverse sine of 18, I just use the insert feature rather than delete. Go to the end here. Then you get the balance. This is about 45.5 rounded. And that should be remarkably close to 180 degrees if you add it. If it's off ever so slightly, it's because it's been rounded too many times. All right, so 52.4 plus 82 plus 45.5 is this, yeah. This, if you were to check it, is 179.9 degrees. It's just shy of 180 because of the rounding, right? Which is why it is not good to round in between, because sometimes you have no choice. Okay. Now, the last thing is Heron's formula. About this. This will work for the purpose of Heron's formula, or Hero, depending upon who you talk to, is to calculate area. Now you might say, well, we already have an area formula. And the area formula is equal to the base times the height divided by 2. Right. However, in that instance, you would need to know the height dimension and the base dimension. Right. You would need to know this perpendicular height, right, and this base. Right. And then indeed you could use it. Now, what if instead you wanted to calculate the area given 3 side dimensions only? You could use this, right? What you need to start with is, it's 2 parts, right? You need to know what is called S. S is the perimeter in half. Right? So if the perimeter of a triangle we'll still call that B just for, consistency. If we're talking about a triangle, the perimeter is the 3 dimensions added, right? Which presumably a person knows if that is what is given, right? And then incorporate that into the actual formula, that is Heron's formula, right? Which is this officially. The area is equal to the square root of S, that's half the perimeter, times S minus A, times the factor of S minus B, times the factor of S minus C. This is the actual Heron's formula, but you would need to find this, which normally you don't know it, right? The half of the perimeter, you know the perimeter usually. Well, if you know the perimeter, you could just divide it by 2 first, right? And then insert it in several places. Let's say hypothetically, you have a situation like this. You don't know what the A is, you don't know what the B is, you don't know what the C is. They would be here, here, and here respectively, if that's what the side dimensions are labeled. If you do know that B is 15, and A is 10, and C is 7, then again, in two parts, figure out what their perimeter is first, which would be 10 plus 15 plus 7, which would be 25 plus 7, which would be 32. And half of 32 would be 16. That's what S is. Insert that, unfortunately, in several places. You have no choice of using this formula. Here, 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 and here. And then put the side dimensions in tandem, in each case. So it's 16 minus 10, and 16 minus 15, and 16 minus 7, apparently. Do the inside of these parentheses first. This would end up being the 16 that was there times 6 times 1 times, what is that, 9. And then you can enter this into your calculator, you get some large number. 16 times 54, whatever that is a huge number, take the square root. Okay, so the square root of 16 times 54 is apparently about 29.4. If I round it, that would be the area. Okay. The area would be about equal to 29.4 units, and since it's an area, it would be squared. Okay. All right. That's basically it. All right. So this is the last section for the semester. What I'm going to do now is, having covered all of the material, is I'm going to give you a final, but obviously I can't collect it. So I'm just going to give it to you and let you have it. All right. And then I'll explain the intricacies of how your grade is calculated in email. Okay. Anyhow, just for the sake of experience, I would try section 10.2 in my open math, whatever specific problems I choose. I'll do that now. But then you could just work on the final for just as a summary, basically, of the material for the semester. And what I plan to do is the last video that I shoot will be I'll walk you through each of the final exam questions. All right, so you see how to do every single type. Okay? All right. Be safe out there. I'll hopefully see you, if not in person, then in spirit, here on Tuesday. All right, take care.